Even nowadays, we have a lot of fancy new words, but this is the very basic things. So all the fecal machine have irrigation, aspiration, vacuum, and pump. Okay. So let's talking about some irrigation infusion. So why we need infusion? Because we need to forming the anterior chamber. As we know, the anterior chamber size about 0.5 ml size, roughly about that. So it has very small volume. So we need to have irrigation inside to form the anterior chamber. Then we can have a movement inside, and also the irrigation can cooling down the fecal tips, cooling down the fecal tips, right? So sometimes we need to increase the irrigation. Sometimes we need to decrease the irrigation. So this is for example, if you're facing the shallow AC, we need to increase the irrigation to have the AC deeper. The higher the bottle height, the deeper the AC. The more pressure, the active bag, the deeper the AC, right? So this is the basic things. And also, when we increase the aspiration, irrigation is the water inside. Aspiration is the water outside of the eye. So sometimes if we increase that aspiration, we need to increase the irrigation also. Because as aspiration more, irrigation keep the same, the AC will shallow, right? So sometimes we need to think about and hemorrhage. Sometimes bleeding, the more pressure will stop that. And the low compliance of the tube. This is the most important things when in the future we are in our hospital. Maybe we are using different fecal machine. So if you see the aspiration tube is so soft, maybe you need to increase the irrigation more a little bit to adapt the surge, adapt the anterior chamber move a lot. Okay, so this is very important. Sometimes we need to decrease irrigation because we do not need that much pressure. For example, post-capsule rupture. When the capsule rupture, we do not keep the very high bottle height. We need to lower the bottle height. But still, we need to keep the irrigation forbidden the vitreous comes out, right? So we still need that, but we cannot make it a higher depth. Because the more depth, that means more pressure, the break part will be extended. Okay, and also something like a high myopia, hyperopia. This all belongs to complicated case. For keep it simple, all the complications we need to lower the AC, lower the pressure, and do it slowly. So this is keep it simple, but yeah. And also when we facing the incision leakage, the water comes out from the incision size. Mostly, some faster choice is increase the bottle height. But if we increase the bottle height, there will be more leakage, and more leakage will cause the anterior chamber more turbulence, because the small nucleus will crack at the leakage place. You cannot easily have the attach for the small pieces. So this time for facing the leakage, lower the irrigation and solve the leakage problem. Sometimes we do have the edema, the incision a little bit. Sometimes we use OBD. Okay. So this is about irrigation. Okay. And now it's the aspiration. We're talking about aspiration. Aspiration is very important factor when we see the nuclear far away. If we increase aspiration, the nuclear comes will be faster. Increased aspiration, the nucleus will come faster. If we increase aspiration, also the holding of the nuclear, the strength will increase faster. So there's two steps: come faster, and we hold the nuclear faster to increase aspiration. But sometimes we cannot, we do not want to that so fast. For example, soft nuclear. If the nuclear is quite soft, like in that lab, it comes, it breaks by the vacuum. Because the nuclear comes, vacuum set up, the force set up, the soft nuclear cannot stand anymore. It disappears inside. You cannot hold the nuclear. So for the soft nuclear, our suggestion is decrease the vacuum, decrease the aspiration, and then you can hold that to fill. For example, for some young patient, very clear nuclear, you cannot treat it as a dense cataract to hold and break. It's not easy, right? So it's like you use chopsticks to hold binker, right? Too much strength, you cannot hold it. You break that. You cannot do the activity well. And also, if we are facing milking is sometimes the emulsification is not enough. It's not enough because of too much holding force. Too much holding force, the nuclear cracked here. There's no space for aspiration. Sometimes we think, there's no space for aspiration. We increase the aspiration, right? But if we increase aspiration, the nuclear will hold too much. There's no space for aspiration. That time we need to decrease the aspiration to let the nuclear loose a little bit, to have more aspiration, to have the milking things absorbed, right? So this is something opposite of our thinking. Also the EPI move to keep safety, okay? So let's see the peristaltic pump design. If the roller rotate, the aspiration comes, nucleus occlude here, vacuum setup. If we want to, the nucleus comes faster, we just increase the aspiration. AFR, aspiration flow rate. Okay. So if we want the nuclear come faster, we increase the aspiration. Okay. If we want to hold the nucleus more strength, we increase the vacuum. Vacuum is responsible hold nuclear how much, and aspiration is responsible how fast it comes and how fast you can hold it. It's about the fast. Aspiration talking about the fast. Vacuum talking about how much. Okay. So let's see the lemon. The nuclear from far away comes to the phaco tips. That's step number one. We call it followability. We call it attractability. So aspiration control how fast it comes to the tip and how fast the vacuum set up. Okay. So the second is vacuum setup. After the lemon come to the tip, the vacuum start to set up. The aspiration responsible the holding force setting up. Okay. Sometimes if you're facing the chatter, the nuclear is far away, come back, far away, come back for traditional ultrasound. So that means followability need increase a little bit to let it push less to against the push, and push coming back faster. Do not lose the nuclear if we're facing chatter. That's for traditional ultrasound. Okay. So vacuum. Vacuum is the third factor of phacodynamics. It is how we can hold the nuclear. If we're facing the soft nuclear, we need to decrease the vacuum because, for example, like we have the chopstick to hold the binker, hold the tofu. If it's too much, it will break. You cannot hold it. You want to hold that, continuous count, lower the aspiration, lower the vacuum. Okay. So sometimes you are facing longitudinal, traditional ultrasound to push nuclear. Ultrasound is push the nuclear, and vacuum is you hold the nuclear. You hold it well, then when you push that, it is not easy to push away. Okay, so this is the factor how you can hold nuclear well. Sometimes we are using different phaco tips. The different phaco tips open size, the different vacuum setting should be. Because the holding surface is very important. The larger the holding surface, the bigger the force can set up by the vacuum. But the larger the holding surface, the less occlusion rate. So something we must balance inside. Okay. Nothing is perfect. And when we're talking about phacodynamic, sometimes we think about the hydrostatics, and sometimes we're thinking about hydrodynamics. When the nuclear is whole, so the whole system, we reach to the vacuum, the whole system will stop. So it's a balance. And there's also another balance. When the nuclear is not coming, the pump system is rotating, is keep going. So this is two balance. But between these two balance, we can see the AC chamber changes because of that. So this is the step number 1 and step number 2. So the LP increased because the nuclear occluded here. Less aspiration, the same pressure about irrigation. And we hold for a while, and then the nuclear emulsified, disappeared. And then aspiration become more. So the anterior chamber, the pressure dropped. Because of the nuclear disappeared, we absorb new liquid. So the pressure lost. So we call that it is surge. We call that it is surge. This is we call it surge. This is always happen when a phaco machine, the system is not good. Right? So when we're facing about surge, this is high risk for PCR, high risk for complications. So we don't want surge. So all our design is to destroy surge, decrease surge, right? And this is for surge recovery. And this is for dynamic IOP, yeah. And for Ventrin and peristaltic are different. So this is the aspiration and vacuum in turn to change. When occlusion happens, vacuum increased, aspiration decreased. Before the occlusion happened, aspiration increased, vacuum do not set up because not occlusion. Vacuum for peristaltic pump, vacuum only happen when after occlusion, and it takes a while to reach the maximum vacuum. Okay, so this is very important for our understanding for peristaltic pump. There's also another pump in the market, we call it Venturi pump. Venturi pump is opposite. Venturi pump only control the vacuum. They do not control the flow. Their sensor is censoring the vacuum, not censoring the flow. Peristaltic pump is censoring the aspiration and censoring the vacuum, both. So when we see these 4 factors, there's some design in the market for irrigation. We not only have the gravity as before, and nowadays we have active pressure goes to the human side. Before we are using the gravity. What is gravity? We use the things job acceleration, which is 9.8 something, right? Nowadays we give different acceleration by machine, press. We can give more, right? Before we can only increase the bottle height to give more pressure. Now we can dynamic to give the pressure to have a stable anterior chamber, so which is more advanced technology. And for aspiration and vacuum, we still have the Ventrin and peristaltic. Now some companies have both and have a switch between. Okay, and for the fecal power. Before we have a longitudinal, now we have a torsional. As the clinical study tells us, the longitudinal, because they are doing things like that, push the nuclear. And torsional is working like this. So we do not need that much vacuum, that much aspiration. We lower the vacuum, lower the aspiration, we do not that much holding force, then we make the anterior chamber more safer. Because we know more vacuum, more aspiration, there will be damage, there will be more surge, right? So the torsional design decrease the perimeter setting. So when we see the longitudinal power, when we see the torsional power, the perimeter setting is different. So torsional not only giving the efficiency, but also give the safety. So this is why we have to design like that. Okay. So now let's talking about something related to the surge a lot, which is, we call it compliance. So if the tube is too soft, what happens? The tube will changing the shape, right? During the vacuum setup. When it's changing the shape, what happens? Take more liquid away. Take more liquid away, because before it's like this, we're setting up the vacuum, the changing the shape, we need to take more liquid. But when it comes back, we take more liquid from the anterior chamber. So the more soft of the tubing, the more surge we will facing during our surgery. So when we're choosing the tubing, please choosing the more hard one, because as we understand, the more harder one, setting up the vacuum faster and less surge. Okay, so when we go back to that wet lab, we can checking the aspiration line is more rigid, more hard. Why? Because we need to reduce surge. Okay. So let's see. That one is more firm. This one is soft. So this one take more liquid from the tube. This one take less liquid from the tube to setting the same vacuum. And when the lemon disappears, which one need to have more flow into the tubing to back to the force, back to the vacuum, zero vacuum. The soft one needs more liquid coming in. So the soft one needs more water coming from the anterior chamber, make more surge, right? So the more rigid one is our, and the vent setting is controlled by the machine. Different company, different design, are design different venting system. For traditional fecal, most of our company design is when our foot pedal from position 2 back to position 1. What position 2 function it was? It is irrigation and aspiration, right? When we back to foot pedal position 1, what will be that?
Irrigation.
Only irrigation. We do not need vacuum anymore, right? We don't need to, the nuclear still hold when we back to position 1. So the machine will automatically venting for us, not in our control. When we touch the foot pedal, go to position 1, it will release the nuclear by machine control. And for our active centric, even during the foot pedal position 3, we're holding the nucleus, and nucleus suddenly disappear. The active centric system will automatically help you to vent, to balance the anterior chamber shake, to give our more stable anterior chamber. So this is the beauty of active centric. I think in the future we are going to use that. Okay. And for reflux, most reflux is controlled by ourselves. If we eat something we do not want, for example, iris, how it split out, we kick the reflux, then it comes out. right? We can setting the reflux pressure by Phacodynamic control. So this is controlled by us, okay? Peristaltic pump, they control the aspiration, they control the vacuum, both. They use the rotate to control how much volume of water and how much pressure by the sensor. So this is the peristaltic pump. They control both aspiration and vacuum. But for the Venturi pump, they only control the vacuum here. They do not control the flow. For the Venturi pump, only control the vacuum, not the flow. So the flow is dynamic. When the flow is dynamic, as we understanding, flow is controlled for what? The nuclear coming speed, right? The vacuum setup speed. If the flow is dynamic, you will see the nuclear come dynamic, the vacuum setup dynamic. So this is different feeling when you use peristaltic pump and Venturi pump. So the parameter setting will be different. Okay. So let's talk about the energy. Before I joined Alcon, I was thinking ultrasound is a sound. Actually not. Ultrasound is the ultrasound frequency jackhammer cracking. It's a real heat, the nuclear. It's not a wave. It's not a wave. It's not Chinese kung fu. It's not that, right? It's a real heat on the nuclear. Okay. Different company, their ultrasound handpiece design a little bit different. But there's a two style. One style is traditional, the other style is torsional. As we mentioned, traditional, a little bit push, so that's why Alcon do not use it in the future. Are going to get rid of the traditional because more heat, more push, more parameter setting, more danger. So Alcon insists on torsional, more efficient, two-way cutting, and less parameter setting for safety and efficiency both. Okay, so this is the basic knowledge. And different companies are using different stroke length. On the screen, we see 30, 70, 100. There's a unit on the back. It's a percentage. Percentage of what? It's the percentage of the stroke length. Different company, the stroke length design is different. Different company, the frequency is different. So we cannot only see the parameter setting to make decision what stroke length, what parameter I'm going to set. We need to know the numbers behind. Then we can compare each company how much energy I'm going to use this machine and another machine. There's no fixed standard. So in the future, we need to have a mindset here. So for example, for all Alcon Phacodynamics machine, the frequency is around 40. So for Elegant and Boschlum, they are using different numbers. So if you are transferred from one machine to another, the parameter cannot copy to one machine to another because the design behind is different. You will facing the continuous burn. You will facing less efficiency if you directly copy the numbers. Okay. So the torsional, how torsional working? We hold nuclear. This is quadrant removal part. We hold nuclear, and the phaco tip is not moving this way. It's moving this way, right? It's like a shaving the nucleus. And two sides doing. Traditional ultrasound is doing one side. Heat coming back, not doing things, but generate heat, right? Traditional ultrasound heat only once, but generate heat on the way back. Torsional doing both ways, right? So more efficiency and less push. Less push, that means less vacuum, less aspiration, less surge, more safety. So that's why for the torsional setting, we have a low irrigation, because irrigation will balance from aspiration. And low vacuum. Vacuum is balance of a holding force and the push, right? And low power, low energy use. Because we are two-way moving now. Not one-way push, one-way generate heat, right? More efficiency. So this is our Alcon recommend parameter setting. But still, we have also traditional Phaco machine for Laureate. For Laureate machine, it's a traditional. It is for the developing market. For example, like China. China need a lot of this because of the machine is cheap, right? So for the irrigation setting, we need to be high, because the aspiration we need to be high to increase the high vacuum faster, to decrease the chatter, right? And we need high power because it's only one way heat nuclear. Okay, so this is the traditional ultrasound. And this is very, very small things, but I see a lot of happen in the market is, do we have a clear numbers for how much phaco tips should be away out of the sleeve? So this is the suggestion from Alcon Phaco machine, based on the stroke length, based on the torsional design. So for traditional ultrasound, longitudinal, we make it 1.5. And for torsional, we make it 1.5 to 1.75, a little bit longer. Yeah, because we are not goes out anymore. We're just moving like this. If we are too short, what happens? If we make it too short, what happens?
Small.
There will be some small leakage here, right? From the irrigation sleeve and tips gaps, right? There's sleeve there. The water will come out. If we make it too short, liquid comes out, will push your nucleus away. You cannot hold nuclear well, right? So there should be standard numbers for the length. If we make it too long, what happens?
Very long.
If we make it too long, when we're doing movement, the irrigation sleeve may be out of the incision. If it's out of the incision, what happens? The AC is only 0.25 ml. So our standard aspiration setting is more than 25. Less than 1 second, your AC will disappear, right? So there's a risk. So that's why that number is very, very important. Okay. Yeah, so this is a different phaco tips and facing different parameter settings. There's a lot of science and design behind. And I'm not going to teach every one of us about this because it takes time to remember and takes time to explain. But I think this is the chart I'm using for our internal training. I train our own staff to learn this, then they can support you in the operation room in the future. So this is the 4 parameters, default basic parameters for Phacodynamics. Okay, so these 4 numbers must be balanced to have more efficiency, more safety. Okay, so don't forget, everything is controlled by your foot pedal. Foot pedal 1 is irrigation, right? Foot pedal 2 is irrigation aspiration. Foot pedal 3 is phaco power. All the machine design is like that. It's a standard design. So just remember that. When you foot pedal from 3 to 2, what decreased? No fecal power anymore. Still you have the holding force. Still you have the holding force. So for example, if you are using fecal chop technique, what foot position you should be? To hold nuclear, to crack nuclear.
3 and 2.
Position 2.
2.
The end of position 2. For the new surgeon, we always very nervous for the first several cases. Very easy to step into position 3 and have the nuclear cracking. That's what we often see. So remember, control your foot pedal well to position 2, then do the cracking movement. That's very, very important. Yeah, this is we often see in the market. And when you're from position 2 to position 1, what happens? The machine will automatically to decrease venting for us to make the anterior chamber stable. Okay, so this is the design. If you more concerned about phacodynamics, no problem. Our Alcon staff is trained to ready for serve you in operation room. Okay, so this is the basic phacodynamic for us. So any questions?